Imagine your engineering team has just spent, I don't know, millions of dollars in compute
Right.
and just months of grueling developer hours building this massive human feedback pipeline to align your new large language model. You're sitting there managing like 4 different models in VRAM just to run proximal policy optimization.
Oh, yeah. It's a nightmare.
It really is. And then right in the middle of all that, a paper drops suggesting that you could have achieved the exact same performance, or maybe even better, using literally just a single spreadsheet.
Yeah.
A spreadsheet of like 1,000 well-curated sentences and a standard supervised fine-tuning run. For anyone working in machine learning right now, I mean, you're listening to this, that is the kind of claim that just makes you stop dead in your tracks.
It really does because, I mean, there's been this prevailing dogma in our field, right? This idea that alignment fundamentally requires just sheer brute force complexity.
Exactly. We all get the unsupervised pre-training phase, on massive trillion token corpora. That builds the statistical foundation.
Right, the base model.
But to make that model act like an actual usable assistant, the industry standard has always mandated these massive instruction tuning data sets. And then, of course, the notoriously unstable RLHF pipeline, reinforcement learning from human feedback.
Yeah, and it is an incredibly heavy operational lift. To run RLHF effectively, you aren't just training one model.
No, not all.
You've got your base actor model, a reference model to calculate KL divergence penalties so the policy doesn't just completely collapse.
Which happens all the time.
Constantly. And then you have a separate reward model trained on tens of thousands of human preference rankings, plus a value network. Mathematically, you are trying to penalize and reward billions of parameters into compliance over this highly complex, constantly shifting optimization landscape.
It's exhausting just talking about it.
It really is. It requires an extraordinary amount of data, and the engineering overhead just to prevent reward hacking or catastrophic forgetting is immense. The underlying assumption has always been that raw pre-training just gives the model like a vocabulary and syntax.
Right.
But the complex RLHF pipeline is what actually instills the reasoning, the safety, and the helpfulness.
And that assumption is precisely what we are scrutinizing today in this deep dive. We're looking at a paper that threatens to just tear down that entire industry dogma.
Yeah, it's a big one.
It's called LIMA, Less is More for Alignment. It was submitted back in May 2023 by Chunting Zhou and a team of 14 other researchers. And they propose a hypothesis that completely sidesteps the RLHF pipeline.
Completely.
They relied on a microscopic data set to answer a really pivotal question. Like, mathematically speaking, how much of a model's capability actually derives from pre-training versus the instruction tuning and reinforcement learning?
Right.
Okay, so let's unpack this. Because if this paper's hypothesis holds, the way we are allocating our gradient updates and, frankly, our engineering hours is just fundamentally backward.
It is a profound departure from the established methodology. I mean, since the Instruct GPT paper, the standard approach assumes that more conversational data and, more complex reward modeling automatically lead to a better aligned model.
More is more.
Exactly. So to rigorously test that assumption, the LLaMa researchers deliberately constrained their training environment to just an extreme degree. They started with a 65 billion parameter LLaMa model.
Okay, 65 billion.
Yeah. And as we know, a parameter space of that magnitude is vast. Normally, to shift the behavioral distribution of 65 billion weights, you'd assume you need a massive gradient signal over, I don't know, hundreds of thousands of steps.
A huge push.
But they entirely bypass the reinforcement learning phase. No reward models, no PPO, zero KL divergence constraints.
Okay, I'm struggling to wrap my head around the math of their alternative, though. If they throw out RLHF completely, what are they actually replacing it with? Because applying a standard supervised loss on just 1,000 examples for a 65 billion parameter model, that sounds like a recipe for immediate model collapse.
You'd think so, yeah. But they replaced the entire complex pipeline with a strictly curated data set of exactly 1,000 prompts and responses. And they fine-tuned it using just a standard autoregressive next token prediction loss. That is the entirety of the LLaMa alignment phase.
Just 1,000.
Just allowed. What's fascinating here is that they're isolating the alignment variable. By removing human preference modeling and the massive dataset scale from the equation entirely, they're testing the absolute limits of data efficiency.
Trying to see what the baseline pre-trained representations can actually do on their own.
Exactly, given only the slightest nudge.
But let me push back on the mechanics of that slight nudge. As a data scientist, if I run standard cross-entropy loss over a dataset of just 1,000 text pairs on a 65 billion parameter model, my immediate fear is overfitting.
Sure.
Isn't that like trying to steer a massive cargo ship with a tiny wooden paddle? The paddle either snaps, or in the ML context, the model just perfectly memorizes those 1,000 specific prompts.
Just grooves right into them.
Right. The gradient updates should over-index on those specific token sequences, leading to these really sharp, narrow, local minima. I would expect it to suffer from catastrophic forgetting regarding its pre-training and just fail to generalize to any unseen prompt. Why doesn't it just collapse?
That tension, the expectation of overfitting versus actual generalization, that is the mechanical core of the paper. Your expectation of overfitting is entirely rational if you view the alignment phase as the period where the model is learning new capabilities.
Or like learning new reasoning skills.
Right. If the model is using those 1,000 examples to learn the underlying logic of how to write Python code or how to deduce cause and effect, then yes, your cargo ship analogy holds perfectly.
Yeah, hey.
A dataset of 1,000 examples cannot generate a broad enough gradient signal to build complex new latent representations from scratch in a 65 billion parameter space. It would just memorize the training set.
So what's actually happening then?
Well, what the LIMA paper suggests is that we have fundamentally misunderstood what alignment is actually doing to the weights.
Meaning, what the latent representations for like Python code and logical deduction are already fully formed.
Precisely. The researchers propose what they call the superficial alignment hypothesis.
The superficial alignment hypothesis.
Yeah. The premise is that all the heavy lifting, learning factual knowledge, logical reasoning, syntax, all those multidimensional relationships that happens entirely during the unsupervised pre-training phase.
Oh, wow.
The model builds a comprehensive internal world model by optimizing for next token prediction over trillions of tokens. Therefore, the alignment phase isn't teaching the model what to think. It doesn't need to learn new skills.
It just needs to learn how to talk to us.
Exactly.
Yeah.
It just needs to learn the specific conditional distribution of tokens that corresponds to a helpful human interaction. So, to extend your metaphor, the cargo ship already has massive momentum and a fully mapped route from pre-training. The 1,000 examples are just the tiny wooden paddle at the rudder, making a microscopic adjustment to the trajectory. You don't need a massive force because the inertia of the pre-trained weights is already doing 99% of the work.
Okay, that makes theoretical sense.
Yeah.
But, planning an alternate history is a neat party trick. If I'm taking this to my engineering manager to justify dropping our RLHF pipeline entirely, I need to know how this model actually behaves when deployed.
Of course.
If it's only doing supervised fine-tuning on 1,000 examples, what happens when it encounters a task that wasn't in that microscopic training set?
Well, it exhibits remarkable zero-shot generalization. The researchers were acutely aware of the overfitting risk, right? So they evaluated LIMA on a holdout set of 300 highly complex unseen prompts.
Okay, 300 unseen prompts.
Yeah. And the model didn't just output generic text, it successfully followed complex formatting constraints and handled intricate reasoning tasks. For instance, it was planning detailed, multi-day trip itineraries with specific logistical constraints, or, like you mentioned, speculating about alternate historical timelines.
Let's break down the mechanics of that alternate history output. Because to generate a coherent alternate history, the model has to navigate really complex latent variables.
It does.
It has to understand cause and effect, maintain chronological consistency, map historical figures to new logical actions. You cannot memorize that from 1,000 unrelated supervised examples.
Exactly. And it proves that the fine-tuning process isn't creating the capability to reason about history. It's just a dress code policy.
A dress code policy.
Yeah, think of the pre-trained model's knowledge space as this vast, multidimensional manifold. It already knows how to dance, how to debate, how to analyze history. That's the pre-training. The 1,000 examples are just the bouncer at the door saying, hey, you need to wear a tuxedo to get into the helpful assistant party.
I love that.
The fine-tuning is merely a low-rank projection. It restricts the sampling space so the model only outputs the specific style and tone of a helpful assistant rather than, say, continuing a prompt like a Wikipedia article or a toxic Reddit thread. The 1,000 examples define the stylistic manifold. They don't teach the underlying facts.
But that implies those 1,000 examples must be incredibly dense with signal.
Oh, absolutely.
If they act as the definitive map to that stylistic manifold, what makes them so special? Did the authors just scrape like 1,000 random instruct GPT outputs?
Not at all. And the curation mechanism is vital to why LIMA actually works. The researchers assembled this dataset with surgical precision to maximize prompt diversity and output quality.
So where do they get them?
They sourced 750 examples from community Q&A forums. Specifically, they selected highly upvoted answers from Stack Exchange and WikiHow.
Oh, that makes sense, because those naturally align with a helpful explanatory tone.
Exactly. But they heavily filtered them for quality. Then the authors actually manually wrote 250 prompts and responses themselves.
Wow, they hand wrote them.
Yeah, they deliberately optimized for a uniform, helpful AI persona, ensuring a really wide distribution of task types without any toxic or low-effort responses. They hypothesized that the density of the quality signal is way more important than the sheer volume of the data.
I see. So if the quality signal is perfectly dense, the model maps to the assistant manifold without needing the iterative penalty cycles of RLHF.
Precisely.
But, okay, for the ML practitioners listening, qualitative examples and theories about manifolds aren't enough. We need to look at the empirical evaluation protocols.
Natural.
How exactly did they measure LIMA against the industry titans? Because evaluating generative text is notoriously tricky. Did they use automated benchmarks or human judges?
They relied on a rigorous, controlled human study, which, is still the gold standard for evaluating alignment quality.
Right.
They generated responses to that diverse test set of 300 unseen prompts using LIMA, and they compared them against responses generated by state-of-the-art models, specifically an RLHF-trained DaVinci 03 model from OpenAI, Google's Bard, and GPT-4.
Let me stop you right there, because human evaluation introduces biases.
It definitely can.
Did they control for length bias? Because models trained with RLHF often game human preference simply by outputting longer, more verbose answers. If human annotators are just picking the longer text, the win rates are completely skewed.
That is a critical point, and yes, the researchers controlled for it. They conducted blind A/B testing, where human crowd workers were presented with a prompt and 2 model outputs and asked to choose which response was better or if they were tied.
Okay.
Crucially, they analyzed the length of the outputs. LIMA's responses were actually often shorter or comparable in length to the baseline models, meaning it wasn't winning just by being artificially verbose.
That's reassuring.
Yeah. They also used a secondary evaluation using GPT-4 as an automated judge to verify the human preferences and the directional trends matched.
Okay, so assuming the methodology is sound, what are the actual win rates? I mean, how does a 65 billion parameter model trained on just 1,000 supervised examples stack up against pipelines that cost tens of millions of dollars?
The statistics are basically a wake-up call for the industry. Against GPT-4, which is arguably the frontier of massive RLHF scale, responses from LIMA were judged to be equivalent to, or strictly preferred over, GPT-4 in 43% of cases.
43% against GPT-4?
Yep.
From 1,000 supervised examples?
Yep.
That is staggering.
And it climbs against other architectures.
Yeah.
When compared to Google's Bard, LIMA was equivalent or strictly preferred in 58% of cases.
Wow.
But the most important comparison is against DaVinci 03. LIMA's responses tied or beat DaVinci 03 in 65% of cases.
Well, here's where it gets really interesting. DaVinci 03 was essentially the poster child for the power of instruction tuning and reinforcement learning with human feedback.
Exactly. It was heavily optimized.
Using the exact complex PPO pipelines we established at the beginning is the industry dogma. Yet LIMA, with 0 reinforcement learning, 0 reward models, 0 human preference tuning during training, beats or ties it 65% of the time.
Right.
Does this empirically prove that the massive RL pipelines the industry relies on are yielding diminishing returns?
If we connect this to the bigger picture, the evaluation data strongly suggests that we have been fundamentally over-engineering the alignment problem.
Interesting.
We've been viewing RLHF and massive instruction tuning as, non-negotiable. But LIMA's 65% win rate over DaVinci 03 proves that extremely high-quality, curated, supervised data can effectively compete with complex reinforcement learning paradigms.
So quality beats complexity.
Yes. The optimization landscape is revealing something profound about data efficiency. The sheer volume of alignment data and the complexity of the loss function matters significantly less than the density and consistency of the signal within the data. We have been trying to solve alignment with massive computational scale when the math suggests we should be solving it with precision targeting.
So if the superficial alignment hypothesis holds true and precision targeting beats massive scale, we have to distill what this implies for the fundamental theory of how large language models actually acquire their knowledge and capabilities.
It's a total paradigm shift.
Because this completely rewrites the mental model of the training lifecycle for any AI researcher.
It absolutely rewrites it. The author's ultimate conclusion shifts the center of gravity in model training. They state that almost all knowledge in large language models is learned during the unsupervised pre-training stage.
The raw text phase.
Yes, that raw text phase is not just building a superficial statistical mapping of token frequencies, it is building a comprehensive, deeply structured internal world model. Therefore, the alignment phase is fundamentally less about injecting new capabilities into the model, and almost entirely about formatting the vast knowledge base the model already possesses.
You only need limited, highly specific data to define that format.
Precisely.
So what does this all mean? For the machine learning engineers listening to this right now, the ones currently managing distributed clusters to run policy gradients, or writing scripts to scrape millions of instruction pairs from the web should they kill their LHF runs today. Should they abandon the scaling laws for alignment and instead spend their next 3 months perfectly handcrafting 1,000 pristine examples?
I would advise a strategic pivot rather than an immediate teardown, primarily to emphasize where the engineering difficulty now actually lies. The LIMA paper strongly supports the less is more philosophy regarding the quantity of data required for high-quality alignment.
Right.
However, it dramatically shifts the engineering burden. It moves the bottleneck from algorithmic complexity like tuning PPO hyperparameters and managing KL divergence to extreme data quality and curation during the supervised fine-tuning phase.
Right, because if you are only using 1,000 examples, a single bad prompt or toxic response carries immense mathematical weight during the gradient updates.
Exactly. The gradient signal is incredibly concentrated. Creating those 1,000 perfectly curated text pairs is not a trivial weekend project.
It's not just copy-pasting from Reddit.
No, not at all. They must perfectly encapsulate the desired tone, structural formatting, safety constraints, and helpfulness of the target alignment manifold. It is an almost artisanal curation process. So yes, engineers should probably stop scraping millions of low-quality instruction pairs because noisy data will actively degrade the alignment manifold.
It'll just confuse the model.
Yeah, but they must prepare to invest heavily in the precise curation of their fine-tuning dataset. The pre-trained model already knows the answer to the user's query. Your 1,000 examples just need to be the flawless cryptographic key that unlocks the correct format.
It is an incredible shift in perspective, really moving from brute force compute to high-precision data curation. To recap the journey we just took, we examined the LLaMa paper and saw how a 65 billion parameter LLaMa model completely skipped the grueling, computationally expensive RLHF phase.
Yep, skipped it entirely.
Instead of managing reward models and reference policies, the authors used a standard cross-entropy supervised loss on just 1,000 meticulously curated text pairs. We questioned the math, fearing that a tiny supervised dataset would cause a massive parameter space to overfit and collapse.
Which is a natural fear.
But instead, driven by the superficial alignment hypothesis, the model demonstrated remarkably strong zero-shot generalization. It handled complex latent variables in tasks like alternate history and intricate trip planning, because the pre-training phase had already built those representations.
Right, the tuxedo at the party.
Exactly. The 1,000 examples merely acted as a dress code, formatting the output, and improved this empirically and controlled blind A/B tests, matching or beating frontier models like GPT-4 43% of the time, and the RLHF trained DaVinci 3 65% of the time. The overarching thesis is clear. Pre-training is where the true capability lies. Alignment is just about surfacing it efficiently.
This raises an important question, though, and it is one that pushes the boundary of this entire line of research, potentially looking past supervised fine-tuning altogether.
Ugh. What's the logical next step?
Well, if 1,000 perfectly curated examples are mathematically sufficient to format the vast knowledge of a 65 billion parameter model, what is the theoretical absolute minimum? We went from millions of RLHF preference pairs to just 1,000 examples with standard supervised loss.
Right.
As context windows grow and inference time compute increases, could future architectures bypass the fine-tuning phase entirely? Could we achieve perfect alignment purely through in-context learning, simply by providing a handful of pristine examples in the system prompt during inference? Where exactly is the mathematical floor for alignment?
Wow. That is the perfect theoretical boundary to leave you with. If we are moving from mass data scraping to pristine curation, how far down does that dataset size go before the manifold mapping just breaks? We want to thank you for joining us on this deep dive into the mechanics of alignment. Keep questioning the dogmas of data science. Look closely at the loss functions and optimization landscapes where your models are actually learning. And definitely take some time to read the LIMA paper yourself to see the prompt curation. And until next time, remember, sometimes the most elegant mathematical solution doesn't require building a bigger computational hurricane. It just requires a very precise nudge to the weights.